By now, you are somewhat acquainted with document store database technology. This deck is intended to help you put it all together from an organizational perspective. Understanding this conversation requires an understanding of previously presented materials. If you get lost, you may need to review the previous slide decks. For example, you should understand the difference between hierarchical and relational data designs. You should know why failover functionality is important when many relatively inexpensive computers replace a single, more powerful one. You should understand what joining is and why it reduces performance in a NoSQL document store. You should have a feel for how data parallelization, partitioning, and replication are used in a document store to increase performance. And you should recall that NoSQL systems relax some burdensome constraints in order to boost performance. Let's begin by admitting that while NoSQL is on the rise, SQL is not going away. Relational systems that organize data into tables with rows and columns are still at the heart of a large majority of organizational systems, and there is no reason for most of these systems to adopt a different structure. The term SQL, Structured Query Language, refers to a language for expressing queries. While it was designed to query relationally organized data, SQL-like query tools are often included in so-called NoSQL systems because SQL is still useful and users still understand it. Many of the valuable innovations built into NoSQL systems are being added into largely relational enterprise-class database management systems such as Oracle SQL Server and DB2. As a result, some of the advantage of adding a NoSQL platform to a portfolio of database tools will be less important as new features are integrated into existing platforms. Some have suggested that NoSQL means not only SQL. Databases can be usefully considered from at least four important perspectives. The external perspective focuses on organizational goals, risks, opportunities, and constraints. The logical perspective emphasizes a precise understanding of the things and events to be modeled and of the relationships between those entities. The digital perspective is all about the technical capabilities of computerized components, including software, hardware, and networks. Logical and digital concerns are integrated to meet external needs in the database implementation. You might say we translate the logical data design into an implementation, bowing to the digital to achieve external requirements. You can't really make good decisions about a database platform without considering all four of these perspectives. Billions of dollars have been spent developing powerful, comprehensive database management system tools such as Oracle SQL Server and DB2. Using out-of-the-box management tools, enterprise-class DBMS can be configured to include robust and efficient backup, data partitioning and replication, comprehensive verified and logged security functions, integrated logging that allows rollback of a series of data updates, specialized programming languages that allow programmers to develop and manage data-centric business logic inside the database, flexible data extraction and loading tools that support data transfer, and much, much more. These systems are designed to do everything well. More recent NoSQL tools, such as Hadoop, Cassandra, and MongoDB, are nowhere near as comprehensive. They have far fewer features and tools. While NoSQL systems lack many features, they promise to add value because of flexible schemas, low cost performance ratios, and incremental scalability. NoSQLs are different in that they impose less structure on stored data. Whereas data in a relational system must be organized to fit into columns created in the database, similar documents in a document store can have different attributes. The NoSQL paradigm emphasizes flexibility over enforced consistency. Let's face it, not all data fits nicely into columns. While images and videos can be saved as column values, and the text of documents such as contracts, patents, or design specifications can be managed by many relational database management systems, the applications that use those resources may not benefit much from the relational paradigm. Further, even when data can be nicely reduced to rows and columns, data formats often change over time or vary in other ways. For example, financial filings with government agencies may include different attributes in different years as regulators respond to legislation or to new understanding. In a relational environment, attributes are relatively fixed. In a traditional database system, administrators tightly control the list of tables and attributes. While the ability to omit or add attributes into an existing data set is not without its risks, NoSQL programmers can add or ignore data elements to adjust to new conditions without modifying existing data infrastructure. Organizations want systems they can maintain at a low cost. Hierarchical documents, such as those often used in document stores, lend themselves nicely to manipulation using object-oriented programming logic. Since programs are designed to accomplish a certain task, hierarchical data makes sense. Well-designed document stores provide all needed data in a single request and accept all needed updates in a single command. This can reduce the amount of code a programmer has to develop. The biggest reason an organization might adopt NoSQL technology is the relatively low cost-to-performance ratio. You can get a lot of bang for your buck. Achieving fast response times for high-volume transaction systems in a relational system requires either lots of money or else a radical refactoring of an organization's data design. If you want to make your relational database faster, there are things you can do. You can denormalize your data sets to reduce potentially costly joining. You can spend a lot of money on random access memory so that most all of the data processing is done in memory. You can ensure extremely fast access to disk storage using storage area network technology. You can install top-of-the-line servers. And you can purchase enterprise versions of the database management software with multiple CPU licenses. Each of those steps can cost hundreds of thousands of dollars for the largest installations. Of course, few organizations need maximum performance, but maximizing performance this way means buying the newest and most expensive equipment. A cluster of computers in a NoSQL system, on the other hand, can be made up of commodity servers. Instead of buying the best to maximize performance, you can buy more relatively inexpensive computers because the system allows for hardware failure and spreads the load across more server units. This commodity server approach also supports incremental spending to achieve incremental increases in scale. An organization can add a couple of servers and increase throughput by a few percentage points as needed, instead of having to write a big check for a big increase in performance. For our discussion today, let's focus on 3 common DBMS features and consider whether or not organizations need them to be part of the data management system. Foreign key constraints ensure that referenced records really exist in the database. For example, invoice records cannot be saved with invalid customer numbers, and the system can block deletion of any customers who have listed invoices. This is called referential integrity. Concurrency controls protect from conflicting updates. If one request tries to add $100 to a bank balance while another is trying to add $200, the system forces one of the actions to wait so that the other can finish. That way the correct final answer is there at the end. Security controls can be set to limit user access to data. So, for example, an accounting clerk might be allowed to see but not change the amount of an invoice, while a sales clerk can create an invoice but cannot post it to the general ledger. Although the database capability landscape changes constantly, each of these features has been compromised in document store systems introduced in the last few years. The thing is that for many systems, these features slow things down without adding value. Forcing the database to verify that a customer number is valid before inserting a new record means extra processing and coordination. This verification requires a join. Joins have negative impact on performance. Often, application programs verified the validity of the record earlier in the process. Why make the database verify it a second time? While protecting a bank account from concurrent changes is certainly important, many, or perhaps even most, data sets are not strongly affected by concurrency issues. For example, only one customer is likely to update any given shopping cart, and if a conflict did arise, it would be a minor annoyance at most. Is it worth it to slow the database down so it can comprehensively coordinate multiple updates? Finally, in big data systems, data is accessed through carefully protected application software. Web-based systems often do all of their database commands for whoever the user is through the same service account. Security is managed in the application, not in the database, so the extra processing associated with security rules is costly but does not add any real protection. These are only 3 examples, but each of these powerful database control features requires that database commands are carefully tracked and managed in real time. To manage concurrency, some one computer has to be aware of all the updates currently in process across the system. To enforce data integrity, a single correct copy of the data has to be maintained, and updates to one list have to be checked against other lists. To ensure security, security rules have to be checked before each action is taken in case rules have changed recently. All of these activities then reduce the independence of each database task and increase the computational cost of coordinating activity. In total, a full-featured database management system consumes a lot of its resources supporting features that are redundant or unneeded in many application environments. The fundamental strategies employed by a document store are focused on completing specific tasks very quickly. The hierarchical data structures, well-designed shards, read-only data replication, and relaxed integrity constraints found in document store databases facilitate lightning-fast response. Organizations often turn to NoSQL systems to manage the load for high-velocity systems where millions of requests and updates need to be processed in a short period of time. Users want systems to respond in a couple of seconds, so it is important that the DBMS do its work in a few milliseconds, because network latency, computation, and page rendering will use up most of the available time window. It would cost a lot more to build a traditional DBMS infrastructure able to provide this level of support while simultaneously managing its logs, validations, and indexing. In today's mobile and web-dominated environments, transaction processing systems are constantly changing. Using a database management system that lets programmers write less code to get needed data and allowing new attributes to be stored without rebuilding infrastructure supports innovation and continuous improvement. NoSQL is agile. These are all reasons to like document stores. But what if different transactions look at data differently? Previous material discussed the benefits of putting all the information for an online shopping cart into a single document. No joins and highly parallel processing means faster response for customers. But what if a retailer also needs to let suppliers quickly access expected product shipment information stored in the customer shopping carts? If the retailer wants suppliers to know how many of its products have been added to shopping carts so that they can plan for upcoming shipments, the customer-focused shopping cart document might be less than ideal. If a supplier logged in to check on demand for its products, the system might have to open every shopping cart document in the list looking for that supplier's products. If 100 suppliers were monitoring demand this way, that would mean that all the shards in the system would be involved in all 100 of the requests. That's a lot of joining activity. It could seriously affect system performance. There are many ways the system could be adjusted to support this task too. For example, additional programming could be done to store demand information in addition to shopping cart documents. Also, document store systems are building in additional indexing capability to help with jobs like this. But, of course, additional programming is expensive, and indexing consumes resources and degrades transaction processing performance. The point is that document stores are usually designed to support specific transactions very quickly, but supporting several kinds of transactions might be slow or involve extra programming. Traditionally organized relational systems aim to support a wide variety of data needs pretty well, but may not be as good at supporting highly specialized, high-velocity transaction processing. Both relational and NoSQL systems optimize for some activities while degrading the performance for others. Our exploration of document store technology has covered a lot of ground. While we have attempted to avoid making specific claims about specific tools, many of the implementation details are constantly changing, so by the time you review these slides, some of the details will be out of date. The biggest trend is that the tools are rapidly implementing features found in competing systems. Enterprise-class database management systems are becoming less rigidly relational, and NoSQL startups are adding valuable features from relational systems. Don't just read the advertisements and endorsements. Make sure chosen systems really meet your needs. Still, the insights should still be valuable to managers and IT practitioners who want to get value from the database management expenditures. Parallel processing can favorably affect the cost-performance ratio for DBMS. Omitting potentially valuable control mechanisms can increase performance, but you need to know what you're giving up. Achieving data management goals takes more than just installation of the right system. Developers need to understand organizational needs. That's the external perspective. Organizations need to understand their data and how different entities relate to one another. That's the logical perspective. Different systems have different technical capabilities. That's the digital perspective. These perspectives all have to be integrated to create an optimal database implementation.